Welcome to today's coding walkthrough. In this session, we'll explore problem number 932, titled Beautiful Array. We'll dive into the problem requirements and evaluate different approaches to solve it, including a brute force method. Let's get started. In this problem, we are tasked with constructing a beautiful array. An array is considered beautiful if, for every pair of indices I and j where I is less than j, there does not exist an index k such that the value at arr k is the arithmetic mean of the values at arr I and arr j. In simpler terms, there should be no triplet I, j, k, with I less than j that satisfies the condition where 2 arr k equals arr I plus arr j. The goal is to generate any beautiful array of size n, where n is a positive integer provided as input. The problem guarantees that at least one solution exists for every valid input. The input consists of a single integer n, ranging from 1 to 10,000. The output should be a list of integers representing a beautiful array of size n that satisfies these constraints. Let's look at a few examples to understand this concept better. For n equals 4, one valid beautiful array is 2, 1, 4, 3. This array satisfies the beautiful array condition because, for every pair of indices I, j, where I is less than j, there is no index k such that the value at arr k is the arithmetic mean of the values at arr I and arr j. For instance, consider the pair 2, 4, where the values are arr 2 equals 4 and arr 4 equals 3. Their arithmetic mean would be 4 plus 3 / 2 equals 3.5. Since there is no index k where arr k equals 3.5, this condition is satisfied. Similarly, all other pairs in this array meet the condition, making 2, 1, 4, 3 a valid solution. In another example, for n equals 5, a valid beautiful array is 3, 1, 2, 5, 4. This array also satisfies the condition that, for any pair of indices I, j, where I less than j, there is no k such that 2 arr k equals arr I plus arr j. For example, take the pair 3, 5, with values arr 3 equals 2 and arr 5 equals 4. Their sum is 6, and half of that is 3. In this array, there is no index k where arr k equals 3. This holds true for all index pairs in this array, ensuring that 3, 1, 2, 5, 4 is a valid solution. For n equals 1, the only possible array is 1, which trivially satisfies the condition since there are no pairs of indices to consider. When the size of the array is just 1, like in the case of n equals 1, the array 1 automatically satisfies the condition for a beautiful array because there are no pairs of indices to evaluate. The constraints of the problem require that the output array must have exactly n elements, and all elements must be integers within the range 1 is n. Additionally, the solution must be efficient enough to handle large inputs, such as n equals 10,000, within the time limits. Edge cases to keep in mind include the smallest input, where n equals 1, as well as the largest allowable input, where n reaches 10,000. The solution should also account for both odd and even values of n, ensuring that no arithmetic mean conflicts arise regardless of the array size. To start, let's consider the brute force approach. The intuition behind this method is straightforward: generate all possible permutations of the array and check each one to see if it satisfies the beautiful array condition. Specifically, for any pair of indices I and j, there must not exist an index k such that 2 arr k equals arr I plus arr j. To implement this, you would use nested loops to iterate over all possible pairs I, j, and then check for an index k within the array that violates this condition. However, the complexity of this approach is a major drawback. Generating permutations of an array of size n takes factorial time, or O, n. And checking the pairwise conditions requires O, n squared, operations for each permutation. Together, this results in an infeasible time complexity of O, n. N squared, making the approach computationally expensive and impractical for even moderately large arrays. This leads us to an optimized solution, the divide-and-conquer approach. Here, the key insight is that a beautiful array can be constructed recursively by separating the array into two groups, one for odd-indexed elements and one for even-indexed elements. By ensuring these groups are built correctly, their concatenation will also satisfy the beautiful array condition. Now, let's delve deeper into the divide-and-conquer approach. The construction begins with an array of size n containing integers from 1 to n. The array is then divided into two parts: odd elements, which are the values at odd indices, and even elements, which are the values at even indices. By recursively applying this division process to each group, we can construct smaller beautiful arrays for these subsets. Once the recursive calls are complete, the results are combined while ensuring that no middle index condition is violated. The efficiency of this approach lies in its structure. The recursion divides the array logarithmically, and each division step requires linear work to split and merge the results. This leads to an overall time complexity of n log n, which is a significant improvement over the brute force method. It's worth noting that while this approach is highly efficient, its correctness hinges on carefully maintaining the properties of the beautiful array during the recursive construction. This balance between efficiency and correctness makes the divide-and-conquer strategy a powerful tool for solving the problem. The divide-and-conquer approach ultimately emerges as the most efficient and elegant solution to the problem. The key realization is that separating the array into odd and even indices inherently avoids any potential violations of the middle index condition. By recursively applying this principle, the problem is broken down into smaller subproblems that can be solved independently. This strategy offers several advantages. First, it is highly efficient, with a time complexity of n log n, making it suitable for large input sizes, even up to n equals 10,000. Second, the recursive construction ensures scalability, as the solution naturally adapts to larger arrays without requiring exhaustive enumeration of permutations. Finally, the elegance of this approach lies in how seamlessly the divide-and-conquer paradigm aligns with the problem's constraints, resulting in a clean and concise implementation. These factors make the divide-and-conquer approach the optimal choice for solving the beautiful array problem both efficiently and correctly. The goal of this problem is to construct what we call a beautiful array from a given set of integers. An array is deemed beautiful if, for every pair of indices I and j where I is less than j, there is no index k such that the value at index k, when doubled, equals the sum of the values at indices I and j. This condition ensures that no triplet within the array violates this mathematical relationship. While this might initially seem straightforward, the key challenge lies in designing an efficient algorithm to achieve this. A naive approach, or brute force, involves generating all possible permutations of the input array. Since an array of size n has n factorial possible permutations, this approach quickly becomes impractical for larger arrays. However, it is important to start by understanding this brute force method before moving to optimized solutions. Once all permutations are generated, the next step in the brute force approach is to validate each one. For every permutation, we examine all pairs of indices I and j, ensuring that no index k satisfies the forbidden condition, 2 times the value at k equals the sum of the values at I and j. If a permutation meets this criterion for all pairs, it is marked as a valid beautiful array. As soon as we identify such a permutation, we can return it as the solution. However, if no valid permutation is found after testing all possibilities, the algorithm either returns an empty array or indicates that no solution exists. To address this inefficiency, we turn to a more optimized approach: divide and conquer. This approach begins by dividing the array into two groups, one containing all odd-indexed elements and the other containing all even-indexed elements. This partitioning plays a crucial role in ensuring that the forbidden condition cannot occur. The divide-and-conquer approach proceeds by recursively constructing the beautiful array. Once the array is divided into odd and even subsets, we apply the same logic to each subset, breaking them down further until they consist of only one element. This recursive process ensures that the subsets remain independent, and no triplets can form the forbidden condition between these groups. After constructing the odd and even subarrays, we combine them, placing the odd-indexed elements first, followed by the even-indexed elements. This combination step maintains the independence of the groups while constructing the final array. When a subarray has only one element, it is inherently beautiful, as there are no other elements to form invalid triplets. This recursive method systematically constructs a valid beautiful array while adhering to the constraints of the problem. The divide-and-conquer approach is built on a few key insights. First, by separating odd and even indices, we eliminate the possibility of forming triplets that violate the forbidden condition. This is because the arithmetic relationship 2 ARR k equals ARR I plus ARR j cannot be satisfied when indices are segregated this way. Additionally, the recursive construction allows us to exploit this separation across multiple levels, ensuring that the solution is built efficiently without testing every permutation. This significantly reduces computational overhead. The divide-and-conquer algorithm operates in n log n time, in stark contrast to the factorial complexity of the brute force approach. In terms of data structures, it primarily relies on arrays for input and output, and the recursive stack to manage the subproblem construction. These insights collectively enable us to handle larger inputs with ease while maintaining correctness. There are three key operations that drive the efficiency of this algorithm. First is the separation of indices, where the array is partitioned into odd and even indexed elements. This operation is linear, O(n), at each level of recursion. The second operation is the recursive application of this logic to the subarrays. The depth of recursion is logarithmic, log n, leading to an overall time complexity of O(n log n). Finally, because the recursive construction guarantees that the output satisfies the beautiful array condition, there is no need for explicit validation. As for edge cases, the algorithm handles them naturally. A single element array is trivially beautiful since there are no pairs or triplets to evaluate. Duplicate values do not pose a challenge, as the separation is based on index, not value. Similarly, an empty array is considered beautiful by definition, as there are no elements to violate the condition. These considerations make the approach robust and adaptable to different input scenarios. In terms of complexity, the divide-and-conquer algorithm achieves a time complexity of O(n log n), thanks to the recursive partitioning and combination of subarrays. The space complexity is O(n), as the recursive stack grows in proportion to the depth of the recursion. To solidify our understanding, let's walk through an example. Consider the input array 1, 2, 3, 4. First, we divide the array into odd and even index subarrays. Odd becomes 1, 3, and even becomes 2, 4. Next, we process these subarrays recursively. The odd subarray 1, 3 is broken into 1 and 3, which are already beautiful, and the even subarray 2, 4 is broken into 2 and 4. Combining these results, we place the odd subarray first, followed by the even subarray, resulting in 1, 3, 2, 4. This final array satisfies the beautiful array condition, demonstrating the effectiveness of the algorithm in a concrete scenario. This Python solution uses a recursive divide-and-conquer approach to construct a beautiful array for the given integer n. The algorithm leverages the key insight that we can separate the problem into two independent subproblems, one for odd indices and one for even indices. The beautiful array function begins with a base case. When n equals 1, the array 1 is already beautiful. For larger values of n, the function divides the problem into two parts. 1. Odd-indexed positions. These are determined by recursively calling the function with n plus 1 // 2, which calculates the size of the odd half. 2. Even-indexed positions. These are calculated by recursively calling the function with n // 2, which determines the size of the even half. The odd and even halves are then mapped to their respective values by the formulas 2*x, 1 for odd indices and 2*x for even indices. These formulas ensure that the resulting array satisfies the beautiful array property, as they guarantee that the arithmetic mean condition cannot be met. Finally, the odd and even arrays are concatenated to form the overall result. This approach is efficient, with a time complexity of approximately O(n log n), and avoids the need for brute force checking of the beautiful property for all pairs. In summary, the recursive structure of this solution efficiently constructs the desired array while maintaining the constraints of the problem. The use of mathematical properties ensures correctness and optimal performance. Here, we begin the Java implementation of the beautiful array problem. The method beautiful array takes an integer n as input, representing the size of the array we want to generate. The first thing we handle is the base case. If n equals 1, we simply return an array containing the single element 1, because a one-element array is inherently beautiful as there are no indices to violate the condition. Next, we use a divide-and-conquer approach to build the array recursively. We split the problem into two parts, one for odd numbers, calculated by calling beautiful array with n+1/2, and one for even numbers, calculated by calling beautiful array with n/2. This ensures that we divide the numbers into two groups based on their parity. Then, we prepare the result array to store the final beautiful arrangement of size n and initialize an index variable to keep track of positions while populating the array. In the loops that follow, we first map the odd indices. For each value in the odd array, we calculate its position in the beautiful array using the formula 2*x1 and add it to result. This formula ensures that all odd indices are placed in the correct order. After handling the odd numbers, we proceed to map the even indices. For each value in the even array, we calculate its position in the beautiful array using the formula 2*x and add it to result. This ensures that even indices are placed appropriately in the array, maintaining the required separation between elements. Finally, we return the result array, which now contains the complete beautiful arrangement of size n. This recursive approach effectively constructs the array by leveraging the divide and conquer strategy, ensuring that the constraints of the problem are met at every step. To begin, we start with the simplest case where n equals 1. The input specifies that the array needs to contain exactly one element. Since there's only one possible way to create a beautiful array of size 1, we directly return the base case result, 1. This is because there are no conditions to violate in such a simple scenario. Now, for n equals 2, the function has to construct a beautiful array of size 2. This means we need to ensure that no element in the array violates the property where for any three indices I, j, k, the value at index j cannot be the average of the values at indices I and k. Let's explore how the function handles this through recursion. To construct a beautiful array for n equals 2, we use a divide and conquer approach. First, we calculate the odd indices. For this, we recursively call the function with input, n+1, divided by 2, which evaluates to 1. Since n equals 1 in this recursive call, we hit the base case and return 1. This gives us the odd indices as 1. Next, we calculate the even indices by calling the function with n divided by 2, which also evaluates to 1. Again, this results in the base case output of 1, providing the even indices as 1. After obtaining the odd and even indices, we map them to their actual positions. For odd indices, the transformation is 2x1, which results in 1. For even indices, the transformation is 2x, resulting in 2. Finally, we combine the two arrays, yielding the result, 1, 2, which satisfies the conditions of a beautiful array. Now let's consider the case where n equals 4. Here, the function needs to create a beautiful array of size 4. Again, we start by calculating the odd indices. This involves a recursive call with input, n+1, divided by 2, which evaluates to 2. For this recursive call, the function evaluates beautiful array, 2. As we've already determined from the earlier example, the result of beautiful array, 2, is 1, 2. Therefore, the odd indices are 1, 2. Next, we calculate the even indices by calling the function with n divided by 2, which also equals 2. Similarly, the result of beautiful array, 2, is 1, 2, giving us the even indices as 1, 2. After obtaining these indices, we map the odd indices using the formula 2x1, which gives us 1, 3. For the even indices, the formula 2x transforms them into 2, 4. With the mapped values, we can now combine the odd and even results to construct the final array. Merging the odd indices, 1, 3, and the even indices, 2, 4, results in the beautiful array, 1, 3, 2, 4. This output satisfies the conditions of the problem because no three elements in the array form an arithmetic sequence. Next, we consider an example where n equals 5. Here, the goal is to construct a beautiful array of size 5. As before, we begin by calculating the odd indices. This requires a recursive call with input, n+1, divided by 2, which evaluates to 3. The function now evaluates beautiful array, 3. For the recursive step with n equals 3, we first calculate the odd indices by evaluating beautiful array, 2. As we've seen, beautiful array, 2, produces 1, 2, which transforms into 1, 3, after applying the formula 2x1. Then, the even indices are calculated by evaluating beautiful array 1, which directly gives 1. After applying the formula 2x, this transforms into 2. Combining these, the result for beautiful array 3 is 1, 3, 2. Returning to the case where n equals 5, we now know the odd indices are 1, 3, 2. For the even indices, we call beautiful array 2, which gives 1, 2. After mapping, the odd indices remain 1, 3, 2, and the even indices are transformed into 2, 4. Finally, we combine the odd and even results to construct the beautiful array for n equals 5. Merging the odd indices 1, 3, 2 with the even indices 2, 4 results in the array 1, 5, 3, 2, 4. This array satisfies the conditions of a beautiful array because no three elements form an arithmetic sequence. The divide and conquer approach elegantly handles the recursive structure of the problem, building larger beautiful arrays by combining results from smaller ones. This completes the construction for n equals 5. To analyze the time complexity of the solution, we start by considering how the problem is approached recursively. At each level of recursion, the input array is split into two parts, one containing elements at odd indices and the other with elements at even indices. The sizes of these subarrays are approximately n/2. These two smaller arrays are then processed recursively. After the recursive calls, the algorithm maps the odd elements to a new array using the transformation 2*x1 and the even elements using 2*x. This mapping step requires iterating over the respective subarrays, resulting in O(n) time for this operation at each level of recursion. Combining these observations, we can already see how the recursive calls and mapping operations contribute to the overall time complexity of the algorithm, which we will explore further. The recursion tree for this solution has log n levels because the input size is halved with each recursive call. At each level, the work required to combine the results of the recursive calls, such as mapping and merging the odd and even arrays, takes O(n) time. To compute the total time complexity, we sum the work done at all levels of the recursion tree, O(n) at the top level, O(n/2) at the next, O(n/4) at the following level, and so on. This forms a geometric series, which converges to O(n). For space complexity, the memory usage is influenced by both the recursion stack and the intermediate results. The recursion depth corresponds to the number of levels in the recursion tree, which is log n, so the recursion stack requires O log n space. In addition to the recursion stack, the algorithm uses some auxiliary space for the intermediate lists, odd, even, and the final result. However, since these lists are reused between recursive calls, there's no permanent additional space allocation during the process. The only extra space required is for the final result, which is proportional to the size of the input and therefore O(n). Combining the space used by the recursion stack, O log n, and the space for the result, O(n), we conclude that the total space complexity of the algorithm is O(n). This efficient use of memory ensures that the solution scales well for larger input sizes. When comparing this optimized approach to a naive one, the efficiency becomes even more apparent. A naive solution would involve generating all possible permutations of the input array and checking each one to see if it satisfies the beautiful condition. Generating permutations has a time complexity of O(n), and testing each permutation requires O(n), resulting in a total time complexity of O(n). *n. This is computationally prohibitive for even moderately sized inputs. In contrast, the divide and conquer approach avoids such exhaustive computation. By leveraging the properties of odd and even indices, it constructs the beautiful array directly in O(n) time and O(n) space, making it a much more practical solution for large inputs. The mathematical foundation of the time complexity further reinforces its efficiency. At each level of recursion, the algorithm processes the input in O(n) time, and with log n levels in the recursion tree, the total time complexity is derived as the sum of O(n) plus O(n/2) plus O(n/4), and so on. This geometric series converges to O(n), confirming the linear time complexity. Additionally, the time and space complexities remain consistent across best, average, and worst-case scenarios due to the divide and conquer strategy, which handles all input sizes uniformly. In conclusion, this approach achieves optimal performance, significantly outperforming brute force methods and demonstrating its scalability and efficiency for solving this problem. Here, we're discussing some of the most common mistakes candidates make when solving the beautiful array problem. First, misunderstanding the problem constraints can lead to significant inefficiencies. For example, if the input size can go up to 10,000, a brute force solution like generating all permutations, which has factorial time complexity, is completely impractical. This approach ignores the constraints and will almost always result in a time limit exceeded error. Next, incorrect handling of edge cases is another frequent issue. Examples include failing to account for empty arrays, single-element arrays, or arrays with duplicate elements. Overlooking these can lead to runtime errors or incorrect outputs. Another mistake is overcomplicating the solution. Sometimes candidates use advanced algorithms or unnecessary data structures without fully understanding the problem. This not only makes debugging harder but can also introduce inefficiencies. Finally, not verifying the beautiful array condition correctly is a critical error. Since the problem often involves specific arithmetic properties, failing to check these precisely can completely invalidate the solution. Logical accuracy in meeting the core conditions is absolutely essential. Another common pitfall is ignoring space complexity. While optimizing runtime is important, overlooking the memory usage of your algorithm can make your solution infeasible for large inputs. For example, if your approach involves creating multiple auxiliary arrays, it might exceed memory limits when handling very large input sizes. With that in mind, let's consider some interview tips that can help you approach this problem effectively. First, focus on the constraints. Discussing them with your interviewer before coding can guide you toward avoiding brute force methods for large inputs. Next, optimize incrementally. Starting with a brute force solution can help clarify the problem, and then you can refine it into a more efficient approach. It's also important to clearly explain trade-offs between different approaches. Compare their time and space complexities and justify your choice based on the constraints of the problem. Lastly, testing edge cases is critical. By proactively considering edge cases during the interview, you demonstrate thoroughness and reduce the risk of introducing logical errors. Now, let's look at some related problems and alternative approaches that can broaden your understanding. First, the beautiful array problem itself is directly related to generating arrays that satisfy specific conditions. Other problems like LeetCode 46 and 47 focus on generating permutations, including handling duplicates in the latter. LeetCode 78, which involves generating all subsets of an array, is also useful for understanding combinatorial patterns that can be applied to similar scenarios. When it comes to alternative approaches, divide and conquer is a powerful technique. Instead of brute forcing the solution, you can divide the array into smaller parts and solve recursively. This is often more efficient, though implementing and debugging it can be more challenging. Another approach involves leveraging mathematical insights. For problems like beautiful array, recognizing specific mathematical properties can lead to elegant solutions with time complexities as low as O, n, or O, n log n. Finally, dynamic programming is another option when the problem involves overlapping subproblems. While DP can significantly reduce runtime, it might increase space complexity, so you'll need to consider the trade-offs carefully. These techniques, combined with a strong understanding of constraints and edge cases, can make your solutions both efficient and robust. Great work! Today, we tackled the beautiful array problem and reviewed the brute force approach, breaking it down step by step. Remember, problem solving is a skill that improves with consistent practice. Thank you for joining me today, and I look forward to seeing you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!